Welcome back. We are on to part two. Okay, we are on to part two. All right, of our Unit 4 applications of derivatives review notes. Okay, we did part one. That was, I don't know, what, 33 or 34 minutes. Okay, part two shouldn't take nearly as long, and this should be it. After this part, for this second video, we should be done with our review of Unit 4, applications of derivatives. Ooh, Unit 5 is integrals, but yeah, we'll wait till we get to that Unit 5 video. Let's get started. Here we go, related rates. Dimensions or measurements that are changing with respect to time. So there might be a change in the radius. There might be a change in the height, etc., in relation or respect to time. So let's just dive right in. The radius of a sphere is decreasing at a rate of 0.5 centimeters per second. What is the rate of change of volume when radius is 20? First of all, we need to figure out what they're asking us for and what, I guess, geometry equation, okay, for area, volume, whatever, that we need to use, okay? And I'm going to tell you this right now. When it comes to basic equations for areas and volumes of a circle, of a sphere, of a square or rectangular prism or a cube, they expect you to know those. This is calculus. But if they are going to tell you to find the surface change in some sort of surface area for a cylinder, they would give you a complicated equation to use if it wasn't a basic one that you should know. Okay, so let's take a look at what they're giving us here. The radius of a sphere is decreasing at a rate of 0.5 centimeters per second. What is the rate of change of volume? Okay, so we're dealing with a sphere. They want us to find the rate of change of its volume. I know the volume of a sphere is 4/3 pi r cubed, okay? We don't want the volume of the sphere. We want the rate of change. Rate of change is the same thing as slope, which is the same thing as derivative, okay? So I don't want volume. I want rate of change of the volume, okay? Now, I got to take the derivative of my equation for volume, all right? Keep in mind that my variable is r, which means that 4/3 and pi are constants, okay? So let's say I didn't have 4/3 pi, okay? That's a rational number, 4/3, and some irrational number, pi. Let's make it simple. Let's say 7. If I had 7r cubed, wouldn't I still bring the 3 down front and then subtract 1? Well, I'm going to do the same thing here, okay? So who cares if it's a 4/3 and it's a pi? Who cares? My 3 comes down, and I multiply my 3 out front, and then I subtract 1, and this becomes a 2, all right? So let's take a look at our constant right now. My 3 cancels with my denominator, and I have 4 pi out front. I have r squared now, but anytime I take the derivative in a situation with related rates, there's always a change of rate, okay? If my volume is going through a change in rate, okay? Ready? Let's do this. Circle, boom, all right? If my circle is going through a change in rate of area or volume, the radius is also going through a change. The radius here, okay, here's the radius, watch this. Here's the line, radius. We'll call this radius 1. If my area, and the same thing for volume, gets bigger, 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 my radius is now a lot bigger, 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 bigger. You see what I'm saying? I mean, look at these two. There's a difference. Okay, there's a difference in those two radiuses. So my radius is going through a rate of change. So my volume is changing with respect to change in my radius. change in radius, a change in rate of radius is like taking the derivative of just radius. Oh, I made such a boo-boo. My change in volume isn't with respect to x anymore. It's with respect to the radius it's changing, okay? So, which means if my radius is changing, there's going to be a change in rate of my radius with respect to time, okay? So I can really say, all right, I can really say my change in volume with respect to my radius. Okay, that equals 4 pi r squared, but my radius is also changing as my time goes by. All right, so I really have, okay, remember when we did, and the best way, I guess, when I teach this to my classes, to kind of relate this to things we've done in the past, no pun intended with the word relate. Remember when we did like y squared plus x squared, we'll call this 3y squared, equals 13, and I had to find the derivative. I had to do this implicitly. The derivative of x squared is, well, that's just 2x. The derivative of 13 was 0. And the derivative of this was not just 6y, but a 6y dy dx. Anytime we took the derivative of the y, we always had to write dy dx next to it, correct? The same thing happens with related rates. Okay, I have to take the derivative of r cubed, right? So I take the derivative of r times dr dx, or in this case, dr dt. Same thing with implicit differentiation. That's the easiest thing I can always bring it back to help you make that connection. So at this point, and that's the most difficult part. We've done the most difficult part already. Meaning, I have some unknowns. I need to solve. They want to know what is the rate of change. I'm solving for this. That means everything on the right side, I should have a number for. Meaning, I should have a number for my radius. I should have a value that I plug in for my change in rate for my radius. And I do, okay? When my radius is equal to 20. So I know that this radius is going to be 20 squared, okay? And then they say this. Do this, do this, do this. I think it was this one, okay? The radius of my sphere is decreasing at a rate of 0.5 centimeters per second. Meaning, this is not the value of my radius. My radius is 20. This is the rate of my radius. And it is decreasing, which means it's negative 0.5 centimeters per second. I mean, it's a rate per time. Per time. Okay? So in here, it's a negative 0.5. That's my rate in which my radius is decreasing. So if I start with a bigger radius, right? And my radius is decreasing. Yep, okay. The volume should be getting smaller. Okay? So, let's just finish off this problem, shall we? We still have 4 pi out front. So 4 pi, radius is 20 squared, okay? And my rate, or my radius is decreasing by negative 0.5. Well, 20 squared is 400. So it's 4 pi times 400 times negative 0.5. That's a half. Half of 400 is 200. And the negative times a positive is negative times 4 pi. And if I multiply all those together, that is negative 800 pi. But what's my label? It's volume. If I label volume, well, we know it's in centimeters. Okay, so it's centimeters. Volume is cubed, but it's a rate that my volume is changing. What's the time? It's in seconds. Okay, so negative 800 pi centimeters cubed per second. That's the rate at which the volume of the sphere is changing right at the moment when my radius is down to 20 centimeters. Okay, so I can write it like this, or I can actually write it as I would answer a person who asked me this question. I can say volume is decreasing at 800 centimeters. Ooh, 800 pi. Ha 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 ha. Centimeters cubed per second. Okay? Because when someone talks to you, okay, well, geez, man, whatever. We're driving to Florida. It's 2,000 miles. I mean, how many more miles do we have left to go? Negative 300. No, he said we have 300 more miles. We're just driving south. Okay? All right? So either one of those answers would be acceptable. Okay? The bottom one is a more logical response. But negative 800 pi centimeters cubed per second is acceptable. Or you can just say that the volume is decreasing. Because remember, when it comes to rates, the negative denotes direction. Okay, in this case, it's decreasing or moving downward. It's getting smaller. Okay, size or direction, decreasing at 800 pi centimeters cubed per second. Hey, hey, hey. A 10-foot ladder leans against a vertical wall. I love drawing these things. The base of the ladder is pulled away from the wall at a constant rate of 2 feet per second. At what rate is the top of the ladder falling when the base of the ladder is 8 feet from the wall? Wow, that's a lot of information. Not really, but Okay, a 10-foot ladder. Here we go, is leaning against a vertical wall. Here's the ground. Green for the graph. Okay. Here is a brick wall. Brick wall because I like to doodle. Whatever. Okay. And we have a 10-foot ladder. Okay. Bada bada bing. Bada bada boom. Ladder, 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 ladder. I know this is a 10-foot ladder. Okay. Now it says a 10-foot ladder. Let me gather all my information here. Is against the vertical wall. Good. That is perfect. And I really don't need that much ground, but what the heck. The base of the ladder is pulled away from the wall at a constant rate of 2 feet per second. This is the base of the ladder right here. It is going to slide this way at a rate. That means that's a dr dt, a d whatever. Let's call this, all right, A, B for base, C. Okay? I don't know what the value from here to here is. I don't. Not yet, anyways. Not at this part in the problem. But I know the rate at which B is changing, dB dt, is 2. Okay? 2 feet per second. If you want to put feet per second here, for the sake of space, I wasn't going to write all these labels. That's 10 feet. Okay? So that B value is sliding to the right. It is growing that distance. The base is moving farther away from the brick wall at 2 feet per second. At what rate is the top of the ladder falling? So they want us to find a rate. Let's go purple. What rate? They don't want us to find A. They want us to find dA dt. Okay. At what rate is the top of the ladder falling down when the base of the ladder is 8 feet? Now they actually give me that. When the base is 8 feet, not when the rate, that's an actual distance, not a rate. So here we go. Okay, right now, I have an A, a B, and a C. Okay, I have a dB, okay, which is my rate. I don't have a DC though, do I? They don't ask us for it, but it seems like maybe I should know that. Okay, I don't have a DC, but they want me to solve for dA. So what equation can I come up with that relates all three of those sides to a triangle? And by the way, I hope you realize that when you make a brick wall, this isn't the Leaning Tower of Pisa. That's a 90-degree. Okay, I have a triangle here. I have a 90-degree triangle. How do I relate the sides of a 90-degree triangle? A squared plus B squared equals C squared. Okay, they want to know the rate dA. That means I'm going to have to take the derivative of all these. Okay, I'm going to have to take the derivative of the Pythagorean theorem. Okay? I'm going to do this just like anything. The 2 comes down, right? So it's 2a. That subtracts and becomes a 1. And anytime I take the derivative of any of these variables, it's like I had to do things implicitly, right? Plus, the 2 comes down, it's 2b times the rate at which b changes equals 2c times the rate at which c changes. Now, here is what seems to be the problem. Okay, first of all, I'm going to do something easy. I could leave everything like this, and I could get the same answer if I take a quick little shortcut. I'm going to divide everything by 2 because they have a common term. It's going to make my number smaller. Bang, bang, bang. Okay, so now I have a dt equals, plus b db dt equals c dc dt. All right? Mister, if I didn't do that, would my answer be wrong? No, but now my numbers are literally going to be half as big as they would have been. It's going to be easier to manage them, okay? So let's plug in what we know. I don't know what A is yet, okay? I don't know what A is yet. They're asking me for dA. I definitely don't know what that is, but that's got to be the variable I'm solving for. Plus, B is 8 times the rate at which B is changing, that's dB dt, that's 2, equals C, which is 10, times, what is DC? Look at this ladder here, okay? This ladder right here, when that slides, okay? When this slides, when it moves back, when it slides, see the bottom just slides out? Does that change, okay? Is a top, that distance never changes. That's a 10-foot ladder. Even if it ends up, boom, flat in the ground, that's still 10 feet. That distance never changes. That ladder, that number 10 is a constant, okay? And what's the derivative of any constant? 0. The derivative, the change in the distance of the ladder is 0 because the ladder is 10 feet. It is a constant. It never changes. That makes this real easy. All right? But here's something that maybe some of you figured out already. Maybe some of you haven't. Maybe some of you forgot. I currently have 0 equals 16 plus dA dt. This is what I'm solving for. But I still don't have A. I can find A really, really easy. How can I find A? I can find A by using the Pythagorean theorem. How come? I have a B value and a C value. I just got to solve for A. Meaning, all right, if I know A squared plus B squared equals C squared, I don't know what A is yet. I know B is 8. And I know C is 10. 8 and 10. If I have 2 sides of a triangle, I can absolutely find the third side. Okay? That means A squared plus 64 equals 100. A squared, if I subtract 64 from both sides, it's 36. So A is 6. All right? So let's continue this. I'm just solving this equation that I have right here. Here, if you need me to go something like that, I'll do that right there. If I subtract 16 from both sides, I got 6 dA. I hate rewriting this every single time, but I'm trying to be a good model here. And I divide by 6, right? Boom. Divide by 6. So dA dt equals negative 16 over 6, which reduces to negative 8 thirds. I'm not going to give a mixed number or anything like that. What's my label? What's my rates? It's feet per second. Question. Should that be negative? What's happening to A? Okay, as B slides this way, the bottom of the ladder, Shouldn't this slide down, which means my distance, right? My distance from here to here is going to be shrinking, isn't it? This distance, okay, right? Let me do this in yellow, even better. Here, okay, to right here. That a distance as the top of the ladder comes down. Look at the distance is shrinking. It's getting closer and closer to 0 once I hit the ground, isn't it? So of course this value should be negative. You can say the top of the ladder, the change in rate of the top of the ladder is negative 8/3 feet per second. Or if we were to answer it like a normal human being, it would be falling. The rate is falling, or the top of the ladder is falling, or the rate is decreasing at 8/3 foot per second, or feet per second, because that would be 2.66 of the line, but we're not going to do all that jazz right there. So negative 8/3 feet per second, or it is falling the ladder, or that distance from the top of the ladder to the ground is decreasing at 8/3 feet per second. We are done, because the rest of this, okay, the rest of this packet, they're problems, they're review problems for you to do, okay? I don't know. Do you like me? Can you give me a like? Can you slap the bell? Just give it a nice little slap. Slap that bell for me, will you? Give it a like. Leave a comment. Ask questions. Do whatever. You know, interact with me. I'm not a computer. I'm actually a human being. And if you leave me a message, I'll get happy, because that means human contact. And then, you know, who knows? Maybe I'll even respond back. But in the meantime, see you later. Have fun. And I will talk to you the next time. Oh my God, it's Unit 5, integration. Second half of the year. But there are a couple of packets, I believe at least a couple, that go along with this Unit 4 that you can try doing on your own after you do the problems that are involved with this note packet. There's 2 separate packets, I believe, that go with this. All right? Have a good time. Like it, share it, ring a ding dong with the bell. See ya.